Today we're going to take a look at a mass on a vertical spring. So in my last video we took a look at a mass on a horizontal spring, but this time we're going to take a look at a mass on a vertical spring. So let's start by drawing a diagram. Let's say I have some kind of, let's switch pen. I have some kind of ceiling over here. This is the roof, and it has some spring that goes like this. It hangs a mass of M. Okay, we're gonna define, let's say we draw something that's here. Let's use a different color pen. It'll be clearer to see. So we draw something that's two line here and two line here, and we call this length right here change in L. This is the spring extension at equilibrium, and then this part from here to here we call unextended spring length. Right? Because when the spring is in horizontal position, when the spring is in equilibrium position, it has some sort of extension. So we define that extension as change in L. And then we draw another diagram. So we just draw, so this whole diagram here is in equilibrium. So now we draw a diagram that's not in equilibrium. Same thing, string. Let's go down even a bit more. So mg, and then we call this distance. So it goes right here. Let's extend this right here. This is L, which is the spring extension at equilibrium. Now we have some displacement x that goes down, right? Like for example, if there's gravity, it somehow, not gravity, but like say you somehow pull the mass down a little bit, it has some displacement which we call x, and that we also need to know that this is positive x direction. So how are you gonna write a differential equation in this case? Well, you do like a force analysis, right? If you look at this case, I'll draw here force. I'm gonna draw a force diagram actually. The force acting on this is gonna be a downward force, that is mg. But remember what I said earlier, that F is equal to negative kx. So the force the spring apply is always opposite to direction of motion. So if direction of motion is the direction of the gravity, our spring will want to oppose it, right? So you could imagine like a real scenario in life. Let's say you have a mass that is attached on the spring and it's hanging on the roof. If, let's say, you put it at an equilibrium position and you let go, right? So what's gonna happen is that gravity is gonna stretch the spring, then it's gonna bounce back a bit, then eventually it oscillates until it reaches the equilibrium position. So we know that the spring force is always against the direction of the motion, and the direction of motion in this case is the direction of the gravity. So we can simply say that the downward force is mg and the opposite force is F is equal to negative kx, just F, right? So here we have for force diagram. So we know that our x in this case is actually not gonna be, our x in this case is actually gonna be the spring extension at equilibrium. We make that equal to mg, and then we again we write g as the second derivative of position. So that's gonna be like m, the second derivative of x is gonna equal to mg minus k times the spring extension at equilibrium plus x. In this case, that's pretty important because our total displacement in this case, right? This is gonna be our x, and our total displacement in this case, as you can see, is actually spring constant plus x. So we're gonna fill that in as there, right? So this is ma. So this is gonna be equal to this is gonna be, let's just expand this. Well, k times spring constant plus kx, and as you can see here, we define these two to be equal. So therefore, this is gonna give us 0. So this is gonna give kx. Actually, no, my bad. Here should have been like a negative x, kx. So this is going to be producing negative kx, and then we move this down here, just going to give m times second derivative of x. Then this is going to be our differential equation for a vertical spring. Perhaps not surprisingly, the result is kind of identical to the equation of motion of my last video, which is a horizontal spring in this case, right? So we simply need to measure this displacement from the equilibrium position of the mass to determine like the acceleration and stuff. Yeah, so this will be a vertical differential equation for a vertical spring. And in my next video, I'm going to talk about a general solution to all of this, like horizontal spring and vertical spring scenario. Because as you can see in each scenario, it has different, what do you call it? Like it has different thing going around. But if you can come up with like a general solution to this equation, it will be much more convenient, which I'm going to do in my next video.